So in this section, section 3.2, we're going to be adding whole numbers together. So there's a few terms that we need to know. So one is the term whole numbers. What in the world are we adding together? So my whole numbers are just all the counting numbers. The counting numbers are numbers you count with. 1, 2, 3, 4, 5, 6, whatever. With a whole. And my whole is my 0. Okay? So 0 through forever are called whole numbers. We're also going to talk about binary operations. So adding and subtracting are called binary operations because we take two numbers and we combine them to make one more number, to make a third number. So that's a binary operation. So when you do addition, we're going to let A and B be what's called two disjoint finite sets. What in the world does that mean? Well, a finite set just means that it ends, right? It's finite. So it doesn't go on and on forever. Disjoint, though, that means that they don't have the same numbers involved in both sets. They don't have any repeats, okay? Disjoint, very different. So, so we're going to add 4 plus 3 equals 7. And so my 4 and my 3 are called add-ins. That's those two numbers that you're going to put together, add together, and your 7 is your sum. So the answer for addition is called sum. Just some neat information. This plus sign first appeared in 1417, and it was a shortcut for writing the Latin word and. It was it. So that's when they first started using plus signs. Okay, so we're going to model some addition. A lot of teachers call addition composing. We're going to compose a number. So we could compose the number 7 with 4 plus 3. We're going to put it together and compose this number 7. You can also decompose a number. So you have 7 and then you break it into its pieces. Okay, so a set model is what you're probably used to thinking of when you think of kindergarten. If I was doing 4 plus 3 in kindergarten, I might do it with gummy bears. And I'd have 4 gummy bears in one set. So that's this one right here. 4 gummy bears in that set and 3 in that set. And then you put them together and you get 7 gummy bears. Okay, so that's called the set model strategy. Let's look at this geeky stuff down here at the bottom, okay? So my geeky stuff, do you see this little N? Okay, the N in front of there just means that's how many numbers are in that set. How many is in set A? So here's set A. So I've got 1, 2, 3, 4. So that's going to be 4. And how many's over here? 1, 2, 3. So that's going to be 3. So when we add those together, that gives us the N of our whole set, okay? And that set, chapter 2 is all about sets. So this is actually chapter 3. So there'll be some geeky set stuff put into this chapter just because it's normally taught right after I teach sets. But anyway, so that's our set model strategy. Let's talk about our number line strategy. First we got to see why set strategy doesn't always work. Okay, the set model. Look at these two sets that we have right here. So we have set A. Notice it has 1, 2, 3, 4 in it. Set B has 2, 5, and 6 in it. Do you notice that these guys both have a 2 in it? So the set model doesn't work very well for this because they're not disjoint. So that means they have repeated numbers. So if I put them together in a set, when you put two things together, you don't repeat anything. So even though A started off with 4 and B started off with 3, when I add them together, since the 2 is repeated, when I add them together, I'm only going to get 6. Do you notice that I only have 6 in that set because my 2 is repeated? So in that case, 4 plus 3 is not 6 unless it's a set model. So it's not disjoint. But if they are disjoint, then it works very well. So let's talk about the number line strategy. Okay, so we're going to use our arrows to represent this 4 plus 3. So the first thing I'm going to do is I'm going to make an arrow that goes from 0 to 4. Okay, then I've got my, I start at 4 and I go on up to 7. So I make another arrow that's 3 units long. So my answer is 7. Okay, now there are other ways that you could write this. So you could do it with humps. Okay, some people do humps. I tend to use straight arrows, but you could use humps. Notice you've got 4 and you've got 3. The key is, if when you're doing it on a test, don't do it like the one I just showed you. Okay, notice that just humps all the way over to 7. Okay, it does not show you that it doesn't show you the number 4 and then the number 3, okay? So you would want to have, you have to show that it stops right here at 4 and then starts again, okay? Now, let's look at the number line, at this number line right here, okay? There's something wrong with that number line. Can you tell what's wrong with that number line? Let me scoop that down a bit. Okay, so what's wrong with that number line is that it did not start at 0. So our number line should have started here and gone all the way, okay? So our number, when we are making those arrows, okay? So our number line started at 0, but when we started counting, we did not start the arrow at 0. And that is a very common mistake for students because they start counting at 1. They don't start counting at 0. But I want to make sure that you don't make that mistake on your test and your students don't make that mistake on their test. Okay. So that's our 2 set model strategies, two models for addition. So the set model where you actually have items that you can put together. You've got 2 sets and then you put them together. And then you can draw it with the number line strategy, okay? So now let's talk about how to add some basic facts. So there's multiple ways of doing it, but we're talking about counting on, doubles, and making 10 first, okay? So remember, what's classified as a basic addition fact means you're going to have a single digit plus a single digit. So 4 plus 3, not 256 plus 973. Okay, those would not be considered basic facts. So this is how you can teach basic facts. So one of the strategies is called counting on. And with this one, you are going to start at one number and count up to the other number. So if I have 14 plus 3, we could do this by starting at 14, and then we're going to add 3. So 14, 15, let me do it with here, 14, 15, 16, 17. And you can use your fingers. Your students can use their fingers. Start at 14, and then they can hold up 3 fingers and do 15, 16, 17, okay, to get to that answer. Now, which is going to be easier to start on? Is it going to be easier to start on the 3 and count up 14? Or is it going to be easier to start on 14 and count up 3? Okay, it's going to be easier to start with the larger number, okay? So when we do 7 plus 5, we're going to start on 7, and then we're going to count up 5. So 7, 8, 9, 10, 11, 12. So, and again, it's okay for your students to use their fingers so that they can keep count of how many numbers they're adding on. Okay, that's called counting on strategy, the counting on strategy. The next one is just doubles, okay? So if you can get students to learn their doubles, they learn what 3 plus 3 is, 4 plus 4, 5 plus 5, and they have those memorized. 3 plus 3 is 6, 4 plus 4 is 8, 5 plus 5 is 10. Okay, so they've got those memorized. Then you can add doubles plus 1. So 6 plus 7, if your student already knows 6 plus 6 is 12. Then they can just add 1 onto it and get 13. So that's what doubles plus 1 is. You add your 2 doubles, and then one of them you're going to add 1 more on. So doubles plus 2, you might imagine, means the same thing. 5 plus 7, if your students know 5 plus 5, they can do the 5 plus 5 to get 10 and then add 2 on. So that's called doubles plus 2. So first they learn their doubles. Then they can add on doubles plus 1, doubles plus 2, doubles plus 3, okay? There's also, you could subtract, but that's not actually in your textbook. But you can actually do doubles minus 1, if that helps. So if they didn't know, like on number 2, if they did not know, the 6 plus 6, but they knew 7 plus 7, they could do 7 plus 7 and minus 1 and get the same thing, get 13. So that's called doubles, or doubles plus 1, doubles plus 2. Now let's do making 10. Students think of making 10 and then add any remaining digits. That's what making 10 means. Okay, so we're going to work with a 10 frame, and this is out of a textbook. So this is, notice this is out of Pearson, down here at the bottom. Pearson, this is first grade, okay? So they're adding some numbers together. So they're going to try and make 10. So you've got, they say 7 plus 4. So we're going to take, let's see if I can get these. Let's see. Yes. So I'm going to get this one. I'm going to add this one, and then I'll add this one. Then I'll add this one. So I've now made 10, and I have 1 left over. So notice that's what we did. So you've got 10 plus your 1 left over, so that's 11. So 7 plus 4, I knew if I added 3 of those 4, I get 10, and then I have just 1 more. That's called this visual thing right here, right there, that's called a 10 frame, and we're going to be using those in class, okay? So notice it shows the same thing here. And this is just straight out of a math textbook for first grade, okay? So here is another visual example. You could use blocks. We're going to use blocks in class. So you could have 8 blocks and 5 blocks. And I'm going to take these 2 out of my 5 and make 10 with it. Right? So I'm going to move those 2 and stick it over here with the other 8, and there's my 10. So I made 10, and then I had 3 left over. So those are a whole lot of pictures for that. But basically, your students would take this, move it over here, and make your 10, and notice I've got 1, 2, 3 left. So 10 plus 3 gives me 13. So that's another way that you can make 10, but without using a 10 frame. You're just using blocks, okay? So here's some making 10 examples just with work. So you've gone from concrete, now we're going towards the abstract, right? So the abstract is going to just be the symbols. So now we have our 9 plus 8, okay? So I know that I just need 1 more to turn that 9 into a 10. So I break that 8 into 1 and 7. And so then I add the 1 to my 9, and that gives me 10, plus my 7, that gives me my 17. Okay, so let's do this example. 7 plus 5, so I'm going to break that 5 into 2 pieces. What would those pieces be? I mean, because you could do 1 and 4, 2 and 3, 3 and 2, 4 and 1. What would you do? I know that I need 3 more to make that 10, right? So I'm going to break it into 7 plus 3 to make the 10, and then I've got 2 left over. So I broke that 5 into a 3 and a 2 so that I could make 10 and then just add my 2. So here's some more information about 10 frames. So before you get to class, you want to watch that video as well. She's got a really great channel, so if you want to subscribe to it, you can. And I want you to, I talked a little bit about what decomposing is, so I want you to write her definition down. Subitizing. Subitizing, what that is, and what in the world is a number bond. You'll see all that in that video. Okay, so now we're going to talk about ordering numbers. So with ordering numbers, that's, putting them in order. So we're looking at the number 4 and the number 7. Notice 4 is to the left of 7, so that means that 4 is less than 7. So the math way of writing it is, right here, is 4 is less than 7. And the alligator, I wish you could see my fingers, but you could make an alligator with your hand like a puppet. Okay, alligator eats the big fish. It's always going to eat the biggest fish. So it's eating 7, so it's going to be pointing to 4, and it's eating 7. So the alligator is going to eat that big fish. That helps your students know which way to face their alligator. Okay, it's also true that 7 is to the right of 4. Okay, 4 is to the left of 7. 7's to the right of 4. That means we can say that 7 is greater than 4. And we write that also using an alligator. Notice my alligator is still eating my big fish. Doesn't matter where the 7 is, the alligator is going to be eating it, and it's pointing to the 4. Okay, we can also say less than or equal to. Okay, so when we do that, we use our equal to mark underneath. So that the first one is less than or equal to. The second one written there is greater than or equal to. So let's see if these are true or false down here. So 3 is the alligator eating the big fish. 3 is greater than 7. Yep, it's pointing to the alligator's eating the 7, so that is a true statement. Here, 3 is less than or equal to 2. Is the alligator pointing to the biggest one? Nope. The biggest one is the 3, and it's pointing to the 2. See, mine. So this is a false statement. Now this one is the alligator. The alligator isn't pointing to the biggest because they're the same. But notice it has an equal to mark over here. So that says 3 is less than or equal to 3. Which, if it was just 3 is less than 3, it would be false. But because it says or equal to, it's true. 5 is greater than 4. My alligator, there's my biggest one, and it's eating the 5. So that's going to be true. And then this one, 5 is greater than 7. 7 is my big one. The alligator is not eating the big fish, so that one's going to be false. Okay. We are going to be using what's called Reckon Recs. Okay, in class, so you're going to need to watch that video. It's about a 9-minute video about what in the world is a Reckon Rec. That's what that little girl has right there. Isn't she cute? Anyway, that's exactly what we're going to be using in class. We're using those Reckon Recs. Your school may not be able to afford Reckon Recs because they're not necessarily cheap, so you can make your own. So here's some ideas to make your own. But I want you to watch that video because we're going to be using Reckon Recs in class, and I won't have time to explain how to use the Reckon Recs. Okay? So now let's talk about some properties. The properties of math. What properties are just laws? Okay? The laws of math. You don't want to break these laws. Okay? That's why I have my little policeman. I'll go after you if you break these math laws. Okay, you've already heard of several of these. You've probably heard of the commutative and associative at some point in your life, but you might have tried to forget about them. But we're also going to talk about closure and the identity property. Okay, so the closure property basically says that, let's say if I have a bunch of whole numbers in this box. So I've got, zeros, ones, twos, threes, and I've got a bunch of them. So I might have some more zeros and ones and twos, and I've got lots and lots and lots of numbers in here. I've got 100, I've got 215, I've got all the numbers from 0 to infinity, and we got them all in there, okay? So if I pick two numbers, any numbers out of there, so let's pick, let me do that one. Let's do a 3 and 100. Okay, I picked those two. If I add those together, I'm going to get, 103. So I've got 103. Would 103 be in my box? It's going to be in my box. It's got all the numbers, all the whole numbers, okay? So that would mean that it is closed. Okay, so A and B are in the whole number box. When you add them together, the answer will have to be in that same box. If that happens, the box is closed. And you don't have to go outside the box to get the answer. Okay, so we can add those numbers and it will be in the box. So let's look at some examples. 4 plus 7. So if 4 is in the box and 7 is in a box, the answer is 11. It's going to be a unique whole number. It's in the box and it shows closure. Okay, so we're going to find out if these next things are closed under addition. Okay, now it's written in a wonky language. It's in set notation. So let's talk about what that says. E is the set 2n, where n is in this box, is a whole number. 2n, 2 times n. I'm sorry, I don't know what happened. Okay, oh, shoot. Okay, well, we will stop the video and I will start another one.